In this lecture, I will talk about two things. One is a very brief introduction to non-parametric estimation, and the second is the introduction to estimating causal effects. Now let's start with a brief review. In week 9, we introduced this linear regression equation, y equals beta 0 plus beta 1 x1 plus da 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 plus beta k xk plus u. And we talked about the interpretation of this linear regression equation in different scenarios. In the next week, week 10, we introduced the OLS estimator for the betas in this linear regression equation and proved the consistency of the estimator under assumptions A1 to A4. For the rest of the course, we are going to assume that A2 to A4 hold. That is, we're not going to question the IID assumption or the finite kurtosis assumption or even the no perfect multicollinearity assumption. So unless otherwise noted, those are assumed to hold, and we will focus instead on A1. That's the orthogonality condition. This orthogonality condition holds automatically for a projection model. If this linear regression is a projection model, that is, this x part is the projection of y on x1 to xk, then assumption A1 automatically holds just by definition of projection. And this we proved in week 9 on page 23. In other words, because we assume A2 to A4 hold and A1 automatically hold for projection, that implies the OLS estimators are always consistent for the projection. The OLS always consistently estimate the linear projection of y on x1 to xk. But of course, whether the projection is an interesting object to study or not, that is another question. But OLS is always consistent for the projection. In the case that the conditional mean of y given x1 to xk is linear, the projection of y on x1 to xk is equal to the conditional mean of y given x1 to xk. In that case, the OLS is clearly also consistent for the conditional mean because the conditional mean is the same as the projection when the conditional mean is linear. But of course, when the conditional mean is not linear, it is not equal to the projection. The OLS is consistent for the projection, but the conditional mean is not equal to the projection. Therefore, the OLS is not consistent. It doesn't consistently estimate the conditional mean function. In that case, it is not linear, so this conditional mean function is not linear. Clearly, adding nonlinear terms will help because that will relax the linearity assumption. Adding nonlinear terms will make assumption A1 more reasonable, like adding interactions between variables or adding square terms. These all could help. For example, when k equals 2, there are two variables, x1, x2, two explanatory variables. We can do an OLS regression of y on x1, x2, and the squares and the interaction. Then that OLS regression will be consistent for the conditional mean if the conditional mean only contains these terms, the linear, the interaction, and the square terms. But of course, this is a weaker assumption than requiring the conditional mean to be completely linear in x1 and x2. but still it is restrictive. How do we know that this conditional mean is of this form? We do not know that. So why these nonlinear terms, not other nonlinear terms? Well, in fact, these nonlinear terms is reasonable in some way. It is a non-mathematical result that any smooth function has a polynomial series expansion. You can expand any smooth function into a sum of polynomials of the function arguments. That is a well-known mathematical result. To give you an example, this function of x can be written as 1 plus x squared plus x cubed plus to infinity. If x is less than, if x is belong to 0, 1. So for any, so this smooth function on the domain 0 to 1 can be expanded into this form, can be written as the sum of all the polynomial terms of x. Another example, the logarithm of 1 minus x can also be written as a sum of polynomial terms, but with different coefficients, with these coefficients. Here, clearly, we also want x to be in the domain 0 to 1. So these are some examples, but the result holds in much greater generality. In fact, any smooth function has a polynomial series expansion. So what is a smooth function? A smooth function, roughly speaking, is a function that you can take derivatives as many times as you want, so infinitely differentiable. If that is the case, then every function, any such function has a polynomial series expansion. Therefore, in the one regressor case, when you only have one explanatory variables, then the conditional mean of y given x, if that is smooth, you can assume that it is smooth in x, then there exists a sequence of coefficients, beta 0, beta 1, beta 2, beta 3, such that this conditional mean is a polynomial function, can be written as the sum of this infinite sequence of polynomials of x times the coefficients betas. So that is a good result. That means you can add these polynomial terms and approximate this conditional mean as closely as possible. Yeah, so if you replace this little x by the random variable x, you can write it as y given x equals beta 0 plus beta 1x plus beta 2x squared plus beta 3x cubed plus to infinity. And this equation exactly holds for some beta values as long as y given x is a smooth function of x. But that is very good. However, we are never going to be able to estimate this infinite number of parameters because we only have a finite sample. With a finite sample, we will not be able to estimate this infinite number of parameters in that series expansion. So in practice, what we can do is to cut the series somewhere. Just throw away what's in the tail, only keep the first kn terms. The justification for that is Once you are beyond a certain term, the remainder will be small. And if we impose some stronger smoothness assumption on this function of x, then we can justify throwing away some of the terms in the tail will not matter. We'll still guarantee that we have a very good approximation to that conditional mean. So we typically cut the series at some point and use the approximation ey given x equals this polynomial function of x. And we estimate beta 0, beta 1, beta 2 to beta kn. And hopefully we have enough data to estimate those. And when we want to justify this, we promise that we will let kn grow once we get more data. And that's exactly what how the asymptotic theory works in a non-parametric regression. So using this to estimate the conditional mean, promising kn to grow as we get more data, is the logic of non-parametric regression. That is, we are not assuming any parametric form for the conditional mean, but instead we use a generic series expansion and promise that we're going to use longer and longer series expansions as we get more data. So that's the basic idea of non-parametric series regression. So estimating the conditional mean by regressing by using ordinary least square regression of y on these polynomial terms is called the non-parametric series regression. And clearly, where do you cut the series is very important. Where do you cut the series? The commonly used class of method is called cross-validation. That's one method that's very commonly used way to choose the cutoff point, Kn. What cross-validation tries to do is to try to minimize the out-of-sample prediction mean squared error. So when you use this Kn number of terms and you estimate a conditional mean, so that's your OLS estimate of the conditional mean, and you want the conditional mean to be close to y. By closing to y, you also get close to the true conditional mean of y given x. You want that to be close to y, and you measure that closeness by the expectation of the square. So that's the prediction mean squared error. You want to minimize this prediction mean squared error by choosing your Kn. Clearly, it's not that the larger Kn you use, the smaller the error will be, because using very large Kn will incur noise in your OLS estimate, because you would be estimating more parameters when you use a larger Kn. Estimating more parameters is more difficult than estimating fewer parameters, and therefore all your estimators will be less accurate when you estimate more. And having noisy estimators will affect your ability to use this linear function of x to approximate y. So larger Kn can hurt this approximation quality in that way, in reducing the accuracy in these estimates. Of course, small Kn also can hurt, because small Kn, the smaller the Kn is, the fewer terms you're using, the less likely you are approximating the true shape of the conditional mean. So the basic idea of cross-validation is to try to find a kn that minimize this squared error, expected square error, trading off these two kinds of noises, right? Trading off the advantage and disadvantage of increasing or decreasing kn. So cross-validation tries to do this, but of course it cannot exactly do it because the expectation is defined using the unknown distribution of y and x, and this expectation is unknown because of that. So it cannot exactly minimize this mean squared error. What it tries to do is to do that approximately. How do you do that approximately? What cross-validation does is the following. It's going to try to estimate the beta using a subset of the available sample. So let's say your sample is y1, x1, y2, x2. Let's say there is only one x variable, so the notation is easier. So y1, x1 is the yx for the first individual and y2, x2 for the second individual to y, say, n over 2 and x n over 2 for the n over 2th individual, and so on and so forth until yn xn to the nth individual. What the cross-validation does, one way to do the cross-validation is to split the sample into two halves, using the first half as the estimation sample. You use this sample to run your ordinary least square for each k. So for each k value, run your OLS using k series terms. Y on x, x squared, 2x to the power k, to get your beta hat k. And once you get your beta hat k, you're going to use this sample. That's your holdout sample or evaluation sample. Use your holdout sample to get a kind of a prediction, which is actually an estimate for the conditional mean for EY given X. But we call it the prediction for each of these samples. YI equals beta K transpose xi squared to xik. For each I in the holdout sample, that's I equals n over 2 plus 1 to n. Once you get this, you're gonna add up or take an average of the holdout sample. You're gonna do an average of the holdout sample. Sum I from n over 2 plus 1 to n. The actual I, for this sample, you have the actual yi, you observe their true yi. You also observe this estimated conditional mean or predicted y. You have both for this sample. And you take the square. And that's an estimate for this out of sample prediction mean squared error. So here out of sample means that this expectation is taken with respect to these y-x random variables, and this and x random variables is independent of the estimators. Okay, you're supposed to evaluate this discrepancy for a sample that you did not use to estimate the beta hats. So that this will be an estimate for this thing. But as you can see, because you have split the sample into two halves, your estimation is based on only one half of the sample, and your evaluation is also only based on half of the sample. And that's considered a waste of data, a waste of information. So what the cross-validation does is, cross-validation has a second step. That is, you reverse the role of the holdout sample and the estimation sample. So one, you're going to do this, and two, reverse the role of estimation and holdout sample. So this estimate of the prediction mean squared error is called, let's say, MK1. And once you reverse the role of estimation and holdout sample, and you do the same thing, you're going to get M2K, which is composed of, so that's K, which is composed of which is composed of the prediction error of the first half of the sample using the estimate obtained from the second half of the sample. And then you average these two. Because now you evenly split the sample, so that's just going to be equal weight average. And that will be your cross-validation criterion. You're going to minimize these criterion to choose your K. So what you do in practice, you try different Ks, say from K from 1 to say 20, and then you calculate this M for these 20 Ks and see which one give you the minimum value of the cross-validation criterion function. So that's the basic idea of cross-validation. Of course, you are not restricted to only split the sample in two ways. You can split it in many different ways. You can use a small, in the extreme, you can split your sample in n ways, and using the n-1 parts as your estimation sample and using the remaining one as the holdout sample. So this is your holdout sample, and this is your estimation sample. Using the estimation sample, you can obtain your estimator, OLS estimator for the betas for each K value. And that will, using that beta, the OLS estimator, you predict the value of Y for this holdout sample. That will give you this Y1 predicted using K for this holdout sample, which is the first observation of the data. And for that observation, you have both the prediction and the true value of Y1. So you're gonna take the difference and square it. So, and then you're gonna rotate which one is the holdout person. So you rotate, say, now the second time you do it, you're gonna use the second kitty as the holdout sample and use the rest as the estimation sample to obtain your beta 2. So all of these are done for fixed K. And then you continue on until you rotated the sample completely. You tried all the possible holdout samples. Say the third time you use the third kitty as the holdout sample and the rest as the estimation sample. And the nth time you use the nth kitty as the holdout sample and the rest as estimation sample. You compute all of these for each K. You compute the prediction for the holdout sample for each K. Compute the error for each holdout sample. And then you add them up. You add all these n holdout samples up to obtain your cross-validation criterion function. You calculate this criterion for a number of different K values and choose the K to be your Kn that minimize this criterion function. So this one is actually this one with a large estimation sample and a holdout sample containing only one individual. This is the basic version of cross-validation. And there are other variations depending on how many observations you hold out. But the idea is pretty much the same. So use cross-validation to choose your K in this way. And I also want to mention that a polynomial series is only one of many ways to expand an unknown smooth function. It's often not the very best one. The reason is that sometimes if your x variable is unbounded, x to a large power, say x to the power 10, will be huge, will be so huge that computer doesn't deal with it very well. So one reason is that x to a large power can get out of control. So polynomial is not always the best thing to do. There are other commonly made choices like B-spline. You can look it up on Google what that is, and Fourier series, and so on and so forth. There are other choices. In Stata, non-parametric series regression can be done using NP-regress series. And if you don't choose an option, Stata is going to use B-spline, but you can also choose polynomial. So the way to do it is to use NP-regress series, your y variable, and then your x variable. If you do not choose any option, then it's going to use B-spline and cross-validation to choose your Kn. You can also specify it to use polynomial. If you do, then it's going to use polynomial series. When you run this command in Stata, it's going to report just one number instead of a bunch of coefficients. that one number is the derivative of ey given x dx, is in fact the expectation of that derivative or an estimate for that derivative. So what Stata reports is an estimate for this expectation of the derivative. But maybe if that's not what you want, what you can do is to add the option E, I think A equations. And then if you add this option, then Stata is going to produce all the beta estimates. And it's going to also tell you which nonlinear terms the cross-validation decided to add to the equation. So that's NP regression. NP regress, you can try to play with it in Stata. And I'm pretty sure that I will not test that in the final exam. Now, a final word on the non-parametric regression is kind of related to machine learning, which you might have heard. Now consider an example with two explanatory variables instead of one. With two or even more explanatory variables, it is still well known that an infinite series of all polynomial terms and all interactions can approximate any smooth function. However, when you have two or more explanatory variables, all polynomial and all interactions, it's kind of very messy. Which ones to include, which ones to include first? It's not so easy to decide. You can use NP regress series to let Stata make some assumptions for you. It's not very clear that those assumptions are super reasonable. Another way to do this is by machine learning. Another way to do this is to include a very, very large number of polynomial or other nonlinear terms and interactions. Possibly you can include even more terms than your sample size at whatever order, doesn't matter. That's the beauty of machine learning. You can include a lot of nonlinear and interaction terms, but of course, ordinary least square will not give you an answer in that case because ordinary least square will not work when you have too many coefficients to estimate. Instead, you can use the penalized least square estimator, which instead of minimizing the sum of squared residue, it minimizes the sum of squared residue plus a penalization term. So in this equation, I want to explain these G functions. These are just known series functions, series expansions of EY given x1, x2. So these are basically polynomial or other nonlinear functions of the two explanatory variables that you have. So this may be polynomial, this may be an interaction, this may be interaction between x and x squared, and so on. You can include many such functions. But instead of ordinary least square, which minimizes the sum of square residue, you minimize that sum of squared residue plus this penalization term, which penalize the size of each of the coefficients. So it tries to not to use speeds that are too large. And what this penalization, this particular penalization does is to make a lot of the b's zero and some of them are non-zero. And this penalized least square estimator is called the lasso estimator. And there are other machine learning estimators as well, but lasso is one of them. It's quite commonly used. It can handle many different explanatory variables as well as many nonlinear terms of them. So I will not give you a lot of details on this. And I believe you have a machine learning course that you can take in the second year. So this is just a teaser of that. Okay, so without further structure, OLS, non-parametric regression, or lasso methods, or other machine learning methods, they all just estimate the conditional mean, or they simply describe how y and x variables are related. Descriptive analysis is very important. Many scientific discoveries start with a correlation, a descriptive finding. For example, this is a true story. Scientists first noticed that people with a rare form of dwarfism, which is called the Laron syndrome, which is caused by a genetic disorder. Scientists notice that people with this genetic disorder tend to actually suffer less from cancer. They get cancer less often than normal people. And that is a correlation, just a data feature. Then, observing this correlation, they started to alter the gene of mice to cause Laron syndrome in the mice. And they found that those mice actually develop cancer less frequently than those whose genes were not modified. So by doing this experiment, following the correlation story, they found a causation story, that the gene governing the Laron syndrome causes the mice to have cancer less frequently. So descriptive analysis can lead to causal discovery. Moreover, many analysis also ends with descriptive results. You don't even go for causal results. You don't even need to go for causal analysis. For example, a fundraising campaign observed that people who contributed previously are more likely to contribute, so that is the correlation. Then the campaign doesn't care whether contributing previously causes more contribution or not. They do not need to care. All they need to know is that this correlation will hold up, and they simply send more letters to previous contributors, and that way they raise more money. They do not need to care whether past action causes current action. All they need to know is that those contributors will contribute more. So descriptive analysis is important in its own right. However, that doesn't stop us from always trying to seek causal relationship. Or maybe that's because in economics, we pride ourselves as students of internal mechanism by which the economy or economic agents operate. We often want to discover causality. So maybe because we want to fix things and we want to change things for the better. And those will require us to learn how the economy actually works. So therefore, we want to know what happens if we change something holding other things constant, and that will require us to learn causal relationship. So in the next video clip, we'll start our discussion of causal estimation.